hopefully be able to see everyone through the lights. I am sitting down because it's very important when you're doing quantum mechanics. You have to look into the smallest parts of matter. So I thought, instead of me looming over you, because I am very tall, we'd just be down here on the table and we'd have a look at a few things. This is the first time I've done this sort of thing, though I've been doing a few demos recently, so we're going to, let's see how we go. But it's a little bit rudimentary, so hopefully this experimental nature of this will be okay for you. And I also want to echo those acknowledgements of country from Peter as well for the Whadjuk Noongar people. And I had the great fortune of going out on country with Dr. Noel Nannup recently, looking at making carbon out of wood. And I was able to show him the nanostructure of the charcoal that we were making to capture carbon from the atmosphere. And we had a great chat about quantum mechanics and all sorts of wonderful things. And it's just wonderful to be able to share in this country. So I want to acknowledge them as well. So quantum for the layperson. My word, what was I thinking? Anyway, let's see how we go. So why on earth did I want to do a talk on quantum? Peter's already talked about it. I find it fascinating. I find it useful. It's also the International Year of Quantum Science and Technology, the UNESCO year. So I just had, I couldn't let the year go without doing a quantum talk. And I think there's some important questions around how ought we to do, how ought we to use the science. So some ethical questions, which I'll touch on. And then what does it mean for faith? And in particular, I'll be talking about Christian perspectives because that's my background, but I welcome discussions with this, and I've actually got some material for different faith traditions on this topic as well if you want to get some more information afterwards. So I thought we would start with the topic of dust, because when you think of quantum, the first thing you think of is dust, I'm sure. But I think that quantum is the science of dust, okay? So that's the idea. And we're going to be going through some different alliteration there. Divisible dust, so we're going to have a look at particles. We're going to be looking at dancing dust, which is going to be waves. Disconcerting dust, which is the quantum weirdness. Designing dust, which is the quantum technology. Devastating dust, you can guess where that's going. And divine dust. So that's the topic. Now, I'm going to spend a lot of time on classical physics. And the reason for that is that I don't think in all of these quantum discussions, it's really hard to get a good handle of what we mean by a particle and a wave. So I'll spend some time explaining what I actually mean by a particle, and then I'll explain what I mean by a wave, at least as a physicist. And then hopefully you'll see why quantum is so weird. Because if I just show you it's a particle and a wave, you're like, oh, cool, that's all good. That makes sense to me. But it really doesn't make sense if you understand what the particle means, the particle perspective, and what the wave perspective is. And the particle perspective will also help us to dive deep into the scale that everything's happening on and really show you just how astronomically small everything is. Okay, great. So some resources if you'd like to know some more about this. The one I'd really recommend is John Polkinghorne. So he was professor of he's still alive, but he was a professor of particle physics, and actually was part of discovering the theory around quarks, which are subatomic particles, which I do not have time to get into today. But he then became an Anglican minister and a theologian as well, much to the surprise of his colleagues. And he's written the most about quantum mechanics. So that is where you should go. There's a very nice book here, a new edition of The Quantum Universe, which is quite nice. And if you want to really get into the maths, Griffiths is a good place to start. All right, so when you're doing physics, I've always heard it said you have to figure out in which world you're working in, okay? And you've got to kind of think about things in a slightly different way. And so when it comes to the small scale, the comic books, this one here, is around the map of the homeworld, the molecular center of the subatomic microverse. So this is an early sort of comic book. And I think I can't quite remember what the, yeah. And And this here is inside of an atomic lattice, and it's talking about the objects that you see speeding past you are streams of endless molecules. And I love the phrase, they call them micronauts, okay? So, you know, if you're doing sort of normal physics, classical physics, you'd be an astronaut. That's a good place to do classical physics. But if you're doing quantum science, you want to be a micronaut, okay? So we're all going to suspend our disbelief, and we're going to put on our helmets and become micronauts, okay? So let's start off with this idea of particles. So I'm not going to go through all of this. More of this is just for reference for those who are interested. Democritus kind of initially talked about this idea of an uncut thing, something that if you keep cutting, it is uncuttable. And this is the idea of the atom. And Aristotle was really unhappy with this idea. He thought that if God could divide things further, he could. And also, philosophically, there's some issues around it, which we'll cover as well, which actually quantum mechanics solves to a large degree. But that is where the term atom comes from, the indivisible thing. And actually what we call an atom these days is actually divisible, so that's going to be confusing as well. All right, so the first sort of hint that there was lots of descriptions of dust moving and what could these things be part of, but it was really when we started to look down microscopes that we started to think of what is kind of in that smallest scale. And Kepler, who was actually very religious, will actually end with a lovely prayer that he wrote for this talk. He was looking at, he actually had nothing to give his benefactor, so he was walking along the Charles River and he thought, I love snow. You know, snow is very nice. Let me write something about snow for my good friend, because what do you give someone who's got everything? A treatise on snowflakes. So he said, why is it that the snowflake, this is a human here, has 6 sides? And he said that there must be some sort of triangular symmetry of the constituents of the molecule. And I've actually got a crystal structure of the water here, and you can see that indeed it's got that trigonal structure. Hooke also looked at different crystals of alum here. So this is a potassium oxide sulfate crystal here. And he saw these faceted edges and said, well, they look like packing of cannonballs, you know. So suggested that this is, it could be made up of small particles. Of course, you couldn't see these. The next thing really came in when we were thinking about air. So really Boyle experimenting with this vacuum pump, which is literally just a syringe, okay? So if you pull on the syringe, you could extract the air, or at least reduce the pressure significantly. And basically by removing the pressure inside of 2 hemispheres, he made something that could not be pulled apart by a team of horses. And so what is causing all of that force? It's the force of the atmospheric air pushing on the outside of the hemispheres, and because you've removed the air inside, there's nothing pushing on the outside. So, and he kind of Boyle talked about that the air pressure is from moving particles. Now, particles comes in here because he didn't like the idea of atoms. He thought, well, surely you could divide those. Or that he didn't really like that idea. So he talked about just small parts, which is what particle means, or corpuscles, which means small bodies. So this is just like dust, okay? And he said the dust, there's some dust in there knocking around, causing that. And this idea of particles or small bodies is really what spurred Newton on to really consider this idea of particles. And his equations of motion, which again, you have to put a space helmet on because they only seem to work properly in space, all right, is that if you have something not moving, it'll stay not moving. And if you have something moving at a certain speed, it will stay moving at that speed in space, unless some force acts upon it. So if you have a little astronaut here, he puts his boosters on, he puts a bit of thrust, he moves faster and faster and faster, this is acceleration, and then he turns off his thrusters. He's going to keep traveling at the exact same speed. And we describe that by the astronaut is a single point, which is basically the center of mass, and we consider an arrow, which is it's the direction, and the length of the arrow tells you the speed, okay? And this is a description, the particle description that Newton described, okay? And so that's pretty weird. And the fact that things go in these orbits around the sun is because they're constantly being acted on by a force which stops them from moving straight. that keeps them going in curved arcs. So Newton sort of described that, and it was, yeah, fairly revolutionary. And I get annoyed when people say quantum mechanics is weird, because that's really weird, right? It's really weird, okay? Just so classical's as, maybe not quite as weird, because we're a bit used to it now. And Newton had a few things to say about bodies. I don't want to say too much here, but basically his idea is that these particles can't wear out. They can't break into pieces. So in a sense, he's defining an atom, something that's reusable, recyclable, and they don't get worn out. And he also talks about how they can attract each other, which is quite interesting as well. So they have these sort of associations and they sort of interact with each other. So he's thinking about these particles that are coming together. So the next really thing is this mechanical view of the world. So maybe these particles are bouncing into each other. And Bernoulli came up with this idea that these little particles are colliding off each other and hitting against the wall, and that is what pressure is. And Joule sort of confirmed this quite nicely by stirring something here and showing that it warmed up. So mixing something, mechanical motion. My favorite example of this is online. You can see a chicken that is cooked by slapping it. So there is a mechanical hand that comes down and hits the chicken, and it takes about 8 or 9 hours, and the chicken becomes cooked. So there we go.
So sad.
The chicken is dead. Sorry. That's a very important thing I should specify. The chicken is dead. All right. Yeah. So this also comes in. Dalton sort of thinks about the fact that when you mix things together, there seems to be proportions in which they mix, and particularly with gases, this is the case. And so Avogadro says, well, maybe there is a sort of a particle that has a specific mass, and let's just say that if we have 16 grams of oxygen, that's 1 mole of these particles. What is mole? Mole just means small mass, so it just means 1 small mass. Using just the fact that these are billiard balls, Loschmidt worked out that the nitrogen molecule is 0.000000. He actually went 9 something millimeters, but the modern value is 36 millimeters. Okay, so that's like the smallest thing you can think of. So imagine having to go 1,000 times smaller. Okay, that's 1 million times smaller. So that's pretty hard to figure out, and the weight is even worse. So won't even read that out. So that's that's very small weight. And the best optical microscopes can do. Oh, sorry. Is this making it hard to see? Is that better? A little bit better. Okay. The best the optical microscope can do is about 0.0002, which is kind of on the order of, sort of like the smallest, like maybe 1,000th of the width of your hair. So it's pretty good. But yeah, we're obviously quite far away. So that's kind of a bit annoying because we can't see it with an optical microscope. Now I've got a little video here that we're just going to skip past the discussion of the diamonds. Here we go. So this is an animation that is looking at zooming inside of a pencil. So this is a pencil made up of carbon atoms, and actually the diamond is made up of the same atoms. And now we're zooming in. And there we are. Wasn't that easy? So let's just try that again, because that's a little bit hard to appreciate. Yeah, there's quite a few boxes there between something that looks familiar and something that doesn't. And you can see that in the case of graphite, you can see these lovely long sheets of carbon that are connected to one another, and that actually is why you can write with a pencil, because those sheets of carbon will wipe off each other. So it's quite pretty. And they're all connected to 3 neighbours, and it makes this hexagonal lattice. So this is the structure of graphite. And if you connect these layers together, which I've been doing recently with a team where we use diamonds to pressurize this graphite, you can actually make bonds between this, and you make a diamond crystal. All right, and the diamond crystal looks like this. So you see the diamond crystal has each carbon atom connected to 4 neighbours. And so they're all sort of connected to one another through these forces that we'll get to soon enough. So maybe we don't need to see single atoms. Maybe we can just see what the atoms do to things. And this is a beautiful story. So Robert Brown actually travelled around the world, including to Western Australia, collected samples of pollen from Western Australia and went back to England, and he was looking at the pollen, actually what's inside the pollen as it germinates, and he saw that what's inside the pollen is jiggling. And he thought, that's weird. And he then sort of just put some dust in there, literally dust, and that also jiggled, and that's an inanimate object. So what's jiggling this dust? You know, that's a big question. And this was quite a puzzle. And so some people tried to think, well, maybe if we can measure the speed at which this particle is jolted, and we know sort of the rough size, maybe we can estimate what is hitting it. And they tried, and it was impossible to measure the velocity. And so Einstein in 1905, in his tremendous year of 1905, you'll be familiar with lots of other things he's done, but he actually proved that atoms exist in this paper, which is pretty remarkable. So Einstein said the particle jiggles because it's being hit by atoms. And instead of looking at the speed, look at how long it travels in a certain amount of time, and do that with lots of particles. And you can get an idea of not only how big the molecules are, but how much they weigh as well in the liquids, which is really impressive. And this actually created the proof that atoms existed. And this was really important. So Perrin did this in 1908. He took a film of this and he took it around the world. And this was the film that really convinced people that there were actually little things jiggling around. So I've actually got that footage here on old film. And you can see these are little particles of, I think they're little plastic beads or some sort of small, something similar to that. And you can see that they're all jiggling around. And if you look at them, they kind of move around in a random walk. And so this footage is basically the thing that proved that atoms existed, which I think is wild, that it was jiggling dust that did that. So that's the first thing I wanted to say, talking about jiggling dust. Now, around this time, people realized that there were also electrons. And Stoney called these an atom of electricity. And so an atom of electricity is an electron. And a nice demo of that is if you charge up one of these evacuated tubes. So we talked about vacuum before. Pull a vacuum on this, and you can actually create a beam of something that when it hits the side of this wall, and you've got a nice chemical there, it will glow green. And this turns out to be a cathode ray tube, and this is a beam of electrons. And this demo here of a, let me see if I can pull it over here. We can demo this at the end, but your eyesight needs to be absolutely pitch black for this to work, and I couldn't quite get it to work. So you can see that there's a cross inside, and you can actually flip that down, and then this here has got a phosphor on it. And so this is what's called a Crookes tube, and you've actually got an electrode here, and the beam of electron comes down here, and then you put the other electrode on this side here. And what you find is that the pattern that's left here is basically you can see the cross basically on it, and that proved, well, they thought it proved that electrons are particles, because if you throw a whole bunch of particles at something and it causes a nice shadow, then of course it's not bending around the outside of it. It's just you're throwing balls at it, and you're either in front of the cross or you're not. And so this was the evidence that was used to prove that, or to suggest that electrons are particles, which we'll find is not right, but it's all right. Yeah, and Thomson found that the mass of these electrons is 1 divided by 1,837 that of hydrogen. So that really small number there, make it smaller by 1,000 basically. So electrons are really, really light. And the charge in the electron was also found to be very small. And the question really then became, well, you've got all these electrons, where is the positive charge? And so Thomson said, well, maybe it's just sort of like a plum pudding. And going through a winter in the UK in Cambridge, there is a lot of plum pudding and Christmas pudding. And so this was probably an unsurprising analogy. So, you know, this is the cake dough, and then the electrons are the fruit that's in the plum pudding. Perrin, who's the guy that looked at the jiggling things, he actually thought that maybe the planetary model is better. So he kind of was inspired by Newton and that, and he said, well, maybe they orbit around. Okay, now everyone's seen that picture, right? Everyone said that's Einstein, right? No, it's not. Einstein didn't think of this. This actually came from, there was a few others that talked about the planetary model, but Perrin actually went around promoting Einstein's idea because he'd shown the results. So in a sense, he publicized it with Einstein's name. So I think they become intimately linked to each other because of that. So Rutherford thought, okay, let's have a look at this plum pudding model, or maybe it's this planetary model, and he threw a whole bunch of radioactive particles. Now, we weren't quite sure what that was at the time, but they knew it was sort of a little bit heavier than hydrogen, and it was positively charged. And so they threw a whole bunch of these small particles, and to their surprise, they found that some of them reflected back. Now, if the charge was all just spread out, they would have all just passed straight through, but because they reflected back, it means that all the positive charge in the atom is concentrated in the center of the atom. And that's what we call the nucleus. And this picture here is actually very bad. This is actually 1 divided by 3,000 diameter of the atom. So in this picture, it would be a single pixel compared to the electrons. So all of the positive charge is here. Now the question is, all these positive charges are repelling each other. It took a lot longer to figure out what was holding those positive charges together. So it was a bit confusing at this stage. So in the end, we had this tiny positive charge in the center, and the electrons are actually spread out. But we've just been seeing that the electrons are particles, so that's very confusing as well. So this is the particle picture here. Particles are localized in space. They have a speed, momentum. You can push on them. They have a weight. They jostle around when they're heated. And it doesn't really make sense when you've got a lot of particles to consider each individual particle. So we come up with these statistical measures like pressure, heat, temperature, other things to describe them. All right, so that was particles. So let's have a look quickly at waves. So waves classically are what a medium undergoes. So if you have lots of water molecules in this case, and you have a surface wave, you'll get ripples that come out off it. Okay. So ripples are a disturbance against gravity. And actually, interestingly, a particle on the top surface of the water undergoes a circular motion. So in a sense, the wave is sort of like a longitudinal wave here, which kind of gets compressed as it goes along, but it's also going up and down. So it's like a transverse wave. And a great way to demo that, I'm going to grab that there. Thank you very much. Is if I push that, then we got the longitudinal wave there, right? And then if I do a little pulse, I can throw it down, which is that transverse wave. So thank you very much. Now, waves can go past each other, and usually they don't interact, at least in the case of water waves. And the other thing that they can do is they can add up when their crests meet, but they can also cancel out if their troughs and crest meet. And that means that you get all sorts of lovely patterns when you're at the beach, because the waves will interact with each other. And when we say these are not aligned, we say that they have a different phase. So that's an annoying word that you just have to commit to memory. Okay? But it describes the fact that there is this additive and subtractive nature of waves. So when we say that it interferes a wave, we're all happy with that, no problems with that at all. We're also familiar with instruments. When you have a wave on a string, you can consider the wave going forward and then being reflected off the other side of the string where it's held, and that wave moves back and forth. Now, if you have a wave moving in one direction and the other, you can actually create a standing wave. And so that's what this is here. Oh, I'll do that one too. That's a good one. Sorry. There we go. So that's the standard one. And if I go a bit faster, you can see at this point there's no motion. So that's a standing wave. All right. Oh, actually that went circularly polarized. We'll get to that. And we don't have time for that. If you put a ringing bell inside a vacuum chamber, remove the air, there's no sound, okay? Because sound moves through air. Great. So that's our picture of sound waves. And this kind of made sense because we just talked about those bouncing billiard balls. This is actually not quite right because these would all be bouncing around against each other. But if you consider each of these points as representing sort of a whole bunch of different particles bouncing around, there's places where they're slightly more compressed and places where they're slightly more further apart. And that's a pressure wave. And actually this idea of sound was around for a long time. Hooke sort of put this into perspective and talked about, well, maybe the air molecules push against each other, so you get this sort of vibrating motion. A little quick look at pendulums. They undergo an oscillatory motion, and that's great for determining time, okay? And the nice thing there is that the length of this, wire here, or the string, and the force of gravity are the two things that describe the speed, at least for small angles. All right, so now we get to light. Sorry, it's been a bit of a journey. Light was really thought to be made up of particles, and Newton kind of said, well, if it was made up of waves, then it would be like sound. If I stood behind a barrier and spoke to you, you'd still be able to hear me because the waves would go around the barrier. But with light, it's a shadow, so of course it's made up of particles. It's not made up of waves. But Huygens basically started off by saying, well, I think it's waves, and also managed to find the speed of light, which is a little bit big, 1 billion kilometers per hour. So that's a bit fast. How do you measure that? I think it was measured a variety of different ways, but basically, I think looking through a toothed cog wheel and making it reflect off a very long, over many kilometers. And the other two ways was looking at different astronomical observations and working out how far away they were, and then you could work out the speed of light. So, so this particle view was what Newton thought, and Huygens was pretty sure that they were waves. And that was really, Young really demonstrated that it was definitely waves by using quite a nice demonstration. So this here is that demonstration. So he put light through a slit, and when you put light through a slit, you get a pattern which actually looks like it's spreading out, and you have little peaks either side of that. Now let me get a double slit here, which is 2 slits. Now this effect looks really great with a laser. It was much harder to do with sunlight, let me tell you. So if you look there, you can see that we've actually got bits where it interferes and bits where it destructively interferes. And that is what waves do, okay? Waves have got the ability to cancel each other out and also to add up constructively. So Young was like, excellent. It's definitely a wave. And my favorite one is the Argo spot. So shining light on a circular target, you actually find you get a little pinprick of light right in the center. And that shows that all the waves come together and converge on a point there. And you can only get that if you've got interference. Electricity and magnetism. Magnets were known for a long time, called lodestones. And Faraday talked a lot about this being sort of a field, okay? A field in which a field describes the interactions of charged particles over long distances, and also connected that to electricity. So as electricity flows, a magnetic field is created, and you can also move things using that magnetic field, and so we have the electric motor. Now this was great. Maxwell came up with the equations for electricity and magnetism, and he found that the speed at which a wave would travel inside that set of equations was the speed of light, which had already been measured. And this was, quite clearly demonstrated that light is connected to electricity and magnetism. And that was a real big win for theoretical physics as well. So let's just have a look at the wavelength of this light, because we can look at the distance between these two peaks and we can kind of consider, well, what's the scale of this? So the scale is 10 to the minus 7 meters. So that is roughly the same scale of atoms. So that's kind of interesting. Down here, sort of atom size. And if you look at the visible spectrum, we're looking at nanometers, or 0.5 microns, which is sort of a thousandth of the width of your hair. So again, really tiny. So when we're thinking about light, we're also thinking about very tiny things. If you move charges back and forth, this is what happens inside of a radio tower. You will propagate waves of electromagnetic radiation. And if you've got an antenna, that wave will slosh the electrons back and forth, and you'll be able to receive that light. Now, polarization is a tricky one, and I wasn't entirely sure how I was going to demonstrate this. Well, we're going to do this with at the very end, I think, if anyone's still interested, because I don't actually have enough glasses for everyone, sorry. So if you get, so basically light is going up and down in one direction in this plane polarized light. But you can imagine that you could have the light traveling in this direction, but you could also have the light traveling in that direction, right? There's no reason why not. And if you were to have two waves, one traveling in this direction, one traveling in this direction, they'd add up, and you would have an oscillation across the diagonal. The next thing that's quite odd is you can have both waves waving at the same rate, or same phase, or you can have one wave slightly offset from the other wave, so that they're doing this, all right? Now, if you actually look at where the electric field is, it does a corkscrew, all right, which is circularly polarized light. And so light is actually quite odd, because it does actually have this ability to have these sort of different interference patterns, these different interactions, which we call polarization. And so that means that you can get some really weird effects. So the weird effect that is an interesting one to demo, and if you come at the end, I can show you this. If you get three polarizers and you cross the polarizers, so I can't actually see any of you right now, so that's this cross-polarized situation. I'm blocking out all the light upright and all the light on the horizontal plane. If I put another another polarizing lens at 45 degrees, I'm actually able to see you now, whereas before I couldn't, which is really odd, right? Yeah. And the reason for that is that when you put in this middle one here, you're actually changing the phase of one orientation, but not the other orientation, so you're twisting the light. So the light's basically splitting up into those two different components, and it's twisting. And so that's actually that's often described as a quantum effect, and it is a quantum effect, but it's also can be described by classical description of light. But it is odd, and that is something that we'll come to in quantum mechanics, which is that the measurement does actually influence it, because there are quite a few different things that describe a quantum particle that are not entirely apparent when you just think about it classically. Okay, so a wave has a size, has a period where it repeats, has a speed, the amplitude of the wave is related to its energy. And the other thing about waves is that the thing that's waving is just going up and down, and the wave is propagating. So you're not actually moving, most of the time, much mass. You're not actually moving anything, whereas a particle is moving something. So that's a big distinction. All right, so disconcerting dust. Quantum things that don't make sense to waves and particle descriptions. So this here is a collection of nice discharge tubes, which I'll show you. I've got some here. But let's start off with glowing dust. So can you pass those out? And I'll pass these out here. Yeah, so just put on the glasses. Thank you. Do you want to just hand those back? Is that all right? Grab two. And I'll just close this for now. Okay, put the glasses on. I've actually got some extra ones here just in case. So they need to be the 500 ones. That's 1,000, 500.
One on each.
Just one. There you go. So if you only have, sorry, there might not be enough. I've got some extra ones here.
That's right, we can share. Yeah.
Yeah, so if you go through those, I've got extra ones here. You can pass those back.
So using these? Yep.
Yep. Yep, sorry, I'll just give you those. Got extra ones here. I certainly have enough for everyone here. Okay, so we're looking. Yep, go for it. Yeah. So if you've got just the single one, then just look, just use it as an eye patch, okay?
Yep.
Sorry. So let me just. Okay, so this here is actually a very old type of bulb. It's called a carbon filament bulb. There's actually not many of these left, but I found it in the physics department. It's made up of a single filament of silk that's been carbonized. And if you look at that now, you'll see it's a lovely red color. Now, if you look through that, through your diffraction glasses, you might be able to see that we've got a rainbow on one side of it. If it's not to the left and right, rotate your grating 90 degrees.
Oh, yeah.
Yeah? Now, what you'll see is at the beginning, see how that's mostly red? And then as I increase the color, the brightness of it, you can see you get more and more blue. See that again? No blue. Now you've got lots of blue. Okay, so this is what's called a black body. So it's something that is black, and then you heat it, and it glows a certain color. Okay, so I just wanted to show you that because it's a bit hard to explain it, and it's a very nice bulb. I like this one a lot. It's the most inefficient bulb. I can feel the heat from here. Yeah. You thought the incandescence tungsten was bad. This is tremendously bad. So as you increase the temperature, it basically becomes more and more. So you can hold on to those. We will need them again. It becomes more and more visible light is emitted. And so for example, a candle actually has black soot in it, but it's glowing yellow hot. So all of these objects here are glowing just because of the temperature. And the challenge was that if you look at classical physics, you would expect that that from Maxwell's solutions and equipartition theorem, which I won't go into, the field should be able to accept any wavelength of light, and it actually should be able to accept wavelengths of light that are at very high frequencies. And so what should really happen is that this should emit an infinite amount of energy in the blue of the spectrum, okay? So classically, it predicts that all of the energy would basically be emitted in high energy photons, and that's the exact opposite of what we see. It actually cuts off. And that's really odd, okay? So Planck was sort of unhappy with this and came up with a solution, but it was sort of a mathematical trick. He said, let me just assume that that once you get to higher energies, we can only emit light in a certain little packet of energy. And so you get to a point where you just run out of energy to emit light. And so you actually get to that point kind of at this range, and then it sort of cuts off. And it was literally a fitting exercise. He had this weird curve, and he put in this parameter, and it fitted the data. And he was like, yeah, that's great, but that doesn't tell me what this thing is. And this is really weird. This is relating energy, which is usually related to kinetic energy of a particle, and it's relating frequency, which is really like a wave. But I just told you that waves, if you want more power in a wave, you amplify it. You increase the amplitude. That's why we have amps with our sound systems. So energy should be related to the amplitude. But in this case, we're saying it's actually related to the frequency. So that was weird. And he was actually quite unhappy with this. And actually Einstein kind of used this effect to actually explain another effect. So if you shine light on a metal, you can actually eject electrons, and you can actually find that at a certain color, like if you go into the green and the red, you can't emit electrons. Now that doesn't make sense, because as I said, energy for light should just depend on its amplitude. So you should be able to shine lots of light on this, and you should be able to get electrons, but you don't get that. You get a cut on where you get a certain color of light that is sort of blue, and then you start to see electrons. And Einstein said that's because the photons, or the light has, each light particle has got a certain energy dependent on its frequency, which is the exact same approach that Planck used. Now that's also very weird, and that doesn't make a lot of sense to the wave picture. And quite nicely, you can actually use this effect to measure a single photon. So this demo, I'm going to attempt to demonstrate a single photon detection with an LED, so wish me luck. So what I have here is I've got a very sensitive electronic device, and it's able to measure things at very fast speeds, nanoseconds, okay? And I've got over here a power supply, and in here I've got an LED, and that LED is connected in the reverse direction as normal, and I'm going to put a whopping great big voltage against it and hopefully not blow it up. But just before it blows up, light coming onto the junction will stimulate the emission of one electron that will then get another one, and you'll get an avalanche of electrons. So let's give that a go. So usually an LED runs at about 3 volts, but we're going to run it all the way up to, I think, 16. Let's give it a crank and see what we do. And fingers crossed. Yeah, there we go. Oh, there we go. Okay, so can you see little jumps there? Sorry. You see little peaks there? So those are individual photons that are hitting that detector. And if I zoom out, and the other thing I can do is increase the brightness of this. And you can see I get slightly more light, and then if I cover this up, oh sorry, oh gosh. Okay, so you get more, and then if I cover that up, it goes away. So there we go. That's a single photon detection with an LED. I actually buy single photon detectors for a lot more than that, so I was very surprised. This is a very inefficient single photon detector, but anyway. That really made things confusing for people, right? Because now you're actually able to see that photons come as little packets, which is really, really quite remarkable. Okay, the other thing I want to show you is atomic emission spectrum. So if you want to put your glasses back on, and you'll see this beautiful glowing tube here. Can you notice that this tube has got very discrete lines here, okay? it's not like, I'll put this one back in so you can see it next to it. Can you see how you see all the rainbow there? But with this, you only have specific light that comes out at very specific energies, and every different type of element, different type of gas, will actually produce different light. So this is argon. Isn't that pretty? And then this is neon. You've seen this before, classic neon bulb. And then this is nitrogen. Sometimes nitrogen's a bit hard to excite, to be honest. Yeah, no, nitrogen has a bit of challenge sometimes. And there we go. This is a mercury light. So we're familiar with mercury lights, yeah. So that's some very nice colors there. Now, something else you'll note here is if I turn on this there, can you notice that that's similar? And if I block that out there, can you see there's discrete lines? Yeah, so this light bulb is actually only creating very specific wavelengths, even though it looks very similar to the other light bulb. So let's put the other light bulb in. And then this is a white light LED. All right, so that's a little bit surprising. So basically, you can see that there's only specific light coming out. Now the reason for that is that the light can only come out at discrete energy levels, which indicates that actually the electrons inside the atom can only be at specific energies. Now this was a real confusion, and Bohr thought, well, maybe let's use this same h, this very small number, and let's just multiply that by the angular momentum. So, angular momentum is to do with things rotating, and angular momentum is a continuous number, but maybe you can only have certain wavelengths or certain momenta. And so he sort of thought about, well, maybe there's a sort of a wave that goes around the nucleus, and then it only meets up with certain particular wavelengths. And so there's only specific orbits. And doing this, he predicted the exact colors that come out. How cool is that? Like the numbers. And there was a nice example of Balmer, who was a teacher and also a devout religious man. He actually worked out the ratio of these here. And so they're called the Balmer lines. And so he literally computed this and then got this exact empirical description. It's very nice. Now, why is orbit a really annoying word to use in this context? Well, I just told you that if charges move, they shake the electromagnetic field, and they should emit photons, okay? So if you had an electron orbiting, it would emit lots of light, and it would lose energy, and it would spiral into the center. Okay, now this, if you don't understand light emitting, is a very hard thing to explain. And so maybe instead of the electron sort of moving around, maybe it's in some sort of standing wave. Maybe it's not moving at all. And I just showed you that. That was if it didn't work. Okay, so De Broglie basically suggested that, well, maybe let's just say that every particle has got a wave, okay? And let's just say that the wavelength is dependent on the momentum and this h constant here, this very small number. And using that, it basically says that every particle has got some sort of wave-like property to it. And using this approach and the mathematics of wave equations, which I would love to go into, but I can't, Schrödinger showed that, that there is an equation that describes these matter waves. Okay, and these are them. Aren't they pretty? This is the different types of ways that the electron can be inside of a hydrogen atom. And each of these transitions, the energy between these levels is the precise energy that you get out when you look at it with those glasses. Now, what does that actual mathematics look like? It looks like this. So you have two things that are waving, and they actually have got, one is an imaginary wave and one is a real wave, which I can't get into, but basically you've got two things waving. There's some internal clock that is running, but if you look at where the electrons are at any given point, we'll talk about this, the probability, they're not moving, okay? So they're not moving, so no light's being emitted, which is great. But there is some internal clockwork going on there. So this was described by Born when he said that the probability of finding an electron at a certain point is given by taking the wave and squaring it. So if I want to know where the electrons are, I will basically just do this wave equation and then compute the square of it and then say the electron is going to be somewhere there. And that is literally what we do. We'll measure it and the electron will be here. And then we'll measure it again. The electron will be here and here and here and here, just like those photons. And then on average, they're in the center. Okay. Weird, right? This Heisenberg, which we'll get to, he was actually quite religious as well and talks about this. This is really uncanny, okay? And the weird thing is that it's got a certain size to it, right? This wave, which means it's got some sort of wavelength and it's got some sort of energy associated with it. But when you measure it, it collapses to a point. And so in a sense, you can't really work out what the wavelength is as well as what the particle is doing. So there's this, it's called the uncertainty principle. You can't know the exact position and the momentum. And the accuracy in which you can determine these is capped by that same h parameter. Okay, so there's a point at which you cannot ask questions about whether it's a particle or a wave. Quite confusing. Position's more of a particle phenomena and momentum is more of a wave parameter in this context. Those functions, which are quite beautiful, they describe the periodic table. So this mathematical function describes the first two rows, hydrogen, lithium, and then if you get these sort of ones that have two sides to them, that describes the carbon, the boron, the oxygen, nitrogen, and then if you get these higher order functions, you get all of the transition metals. So this one equation explains the whole periodic table. It's pretty good. So let's just get onto this light bulb we just saw. So that light bulb has got specific different light that comes out. This is the highest energy electron in the mercury atom. And that, if it wants to go into this state here, which is one of those ones which is sort of split like that, we call that a p orbital. What it does is these two waves will start to interfere with each other and they'll go into an oscillation or a resonance. And that will mean that sometimes they're in phase, sometimes they're out of phase. And that means that they actually the electron density does shift from one side to another. So this can emit light. So these two will resonate and emit light. And these two can resonate and emit light. And likewise, all of these can go into this resonance. And you can see that the probability of finding the electron does change with time, and that will emit light. Okay, so the double slit experiment is the next thing I just want to go through. So we sort of talked about that in terms of waves, right? The waves have interference patterns. They'll constructively interfere, destructively interfere. That makes sense because the wave goes through both of these, comes out in spherical waves, and it interferes. If you have particles going through, if you were to blow sand through two slits, you would see two piles of sand at the end. What happens with photons? So, and we do this in the lab. We've got a third year lab that does this. You turn down the light, so you see a single photon hits the detector at a time, just like we just saw. But over time, you see that we build up an interference pattern. Okay, so why is that so weird? If they're coming through, we're detecting it one at a time. So it can't be the case that one is interfering with another one. So they're all coming, well, we're not quite sure what they do, but it appears as if they are going through and they have to go through maybe one slit or the other slit. But the fact that they make an interference pattern makes it seem like they've gone through both slits. Puzzling, very puzzling. Okay, so photons are weird, okay? Maybe it's just photons are weird. do it with electrons. Single electrons. They make interference patterns. You can do it with an entire molecule. That really is wild, okay? This is a molecule, okay? 60 carbon atoms in a ball. Put that through 2 slits, you get a pattern. It looks like this whole molecule has been able to turn into a wave and interfere with itself. But okay, so that is very odd. So let me just show you the most recent interpretation of this, which is called the Copenhagen interpretation. So particles, as mentioned, go through and just scatter off it, and you get a pile of different things. Waves. Patience, Jake, patience. A wave, it's rippling, goes through both, creates 2. It's actually important that the wave has spatial coherence, which means that it comes from the same point, so that the waves here are in phase, and then the in-phase waves will interfere. Okay, what does a quantum object do in the Copenhagen interpretation? Schrödinger equation, Schrödinger equation, Schrödinger equation, Schrödinger equation. Wavy, wavy, wavy. You measure it, the probability it's there. Waves, it goes there. Collapse. That's just the Born rule. Why does it collapse? Okay. Okay, this is really weird. If you measure the photon, if you measure it here, you lose the interference pattern. Okay, so you might say, well, let's just look at whether it goes through the left and the right. If you do that, because there's energies, any way of looking at it's going to disturb it. You're going to measure it going through one or the other, and it's going to look like particles, no interference pattern. It's like the particle's shy. Oh, let's do the thing again. Okay, Schrödinger's cat. Sorry, cat lovers, this is for dogs. So Schrödinger he did this equation and it worked, but he was still really unhappy with this probabilistic nature of it. Why is it that you measure it and then it just randomly is somewhere? It didn't make sense to him. And just like Planck, he wasn't happy with the theory he came up with. Physicists are, it's a common problem with the job. You don't like your own theory. So he came up with this idea that's quite nice. He said, let's have a box and let's put a cat in there. You should really call SPCA here because the cat will definitely die. There's a radioactive source that will trigger a Geiger counter, and that will release a bottle of cyanide, killing the cat. Okay. Now, if you have the Schrödinger equation, you don't know when this will emit, so it's in a superposition, which means that it could be alive or could be dead. Okay, that's the wave function. Let's just say. But if you open the box, you'll see that the cat is alive or dead, and so you will have collapsed the wave function. And so he said that's stupid. The cat will either be alive or dead. So why are that this is stupid to have this probabilistic effect. And this gets into some really weird stuff where you say, well, is the act of observing going to cause the change in the universe? That's whole sort of stuff. Most people now think that's not the case, and the reason is that basically this. The reason is that the quantum systems will actually become decohered, which means that the cat doesn't need you to open the box to be measured. There are gas molecules hitting it and lots of other things that are going to disturb this quantum system. That will mean that you don't need to measure it, something else will. And so that's called decoherence, and that just shows you that quantum effects are not able to be easily scaled up to this. I showed you a molecule. That is the biggest thing we've done. Okay, that's not a cat. So cat lovers, it's okay. We won't be killing any of your cats anytime soon. The thing that really annoyed Einstein was that you could get 2 particles and you could actually put them into the superposition. You could separate them apart And then by measuring one of them, you would know the situation for the other particle, okay? And this is what he called spooky action at a distance. And that is quite odd, okay? Quite odd effect. So this basically shows that any sort of theory that we can come up with has to be non-local. So we can affect change across the universe in a way that's non-local. There are other options to describe this, but those other options require multiple universes, which is a little bit challenging for some physicists to agree with that. We'll get into that. Won't go into decoherence. I'll leave this up. There are many interpretations, and I am not qualified to talk about them. Okay, so let's just shut up and compute, according to David Merman. So what can we do with this fun quantum stuff? We can make switches, and those switches can be turned into computers. That was pretty useful, and that came directly from this theory, quantum theory of solids. We can make electron microscopes, so we can look at very small samples. Here's me in my happy place. There's an electron microscope. Let's look at some dust. There is the dust under the electron microscope. This pattern is called a phase contrast image. This is the electrons interfering with themselves and the atoms, and that's how we image this. Here's some graphite. It's a picture I took. Each of these dots here is a single carbon atom, which is really lovely. When you put lithium inside of graphite, it becomes a metal. That's also described by quantum theory, and that's how your lithium-ion battery works. And this is part of my research. And you can see it turns a beautiful golden color. Also, you can describe that using Schrödinger's equation. I do it often. Put it in the computer. It comes out gold, which is very useful. We made solar photovoltaics, lithium-ion batteries, the royal we here, LED lights. And actually, a lot of these were, so I had a chat to Colin Humphreys, who is a professor in Cambridge, who did a lot on looking at these under the electron microscope. And he actually also wrote a paper on dating the crucifixion according to astronomical measurements. The lithium-ion battery, John Goodenough, who was one of the Nobel Prize winners for the lithium-ion batteries, who just recently passed away. He was also a strong Christian. So that's an interesting connection there. The other one with the solar PV on your roof, a lot of that was designed in Australia, University of New South Wales, Martin Green's group. They created the technology here using quantum science that enables us to have very, very efficient solar photovoltaics. Lasers, another one of my happy places. I mean, how cool are lasers? You can get a light bulb concentrated into a beam and cut through metal. Tremendous. I can't go into that. Nor can I go into scanning probe microscopy, but if you want to look on my website, we can take images. I work with IBM. We can take direct images of molecules using very, very sensitive equipment, and we can also directly image their electrons as well, using this tunneling effect, which is nice. Superconductors, which I also can't go into in a lot of detail, but these are materials that do not have any resistance, and so you can flow electricity through it with no loss in energy except for the cooling requirements. And these are used to do the most sensitive magnetic measurements, and you can measure rocks well underground using this sensitive technique. So Kathy Foley, our previous chief scientist, developed this and was able to find big reserves of rocks. So quantum science gave us rocks, so everyone here should be very happy. Geologists, excellent. Quantum computing would be a whole other talk, so let's not do that. But in a sense, the classical computers are made up of those switches, which were also developed by quantum theory of solids. But when we want to use quantum computers, we actually want to describe using the quantum effects. And there's a very nice talk from Jingbo Wang, who did a TED talk on this. I recommend looking at that. She's an expert professor of quantum computing at UWA, and it's a very nice description of this. But more or less, you can create these quantum states, these superposition states, and you have to make sure that they do not collapse. So you have to cool this down to incredibly low temperatures, and it's just a real nightmare. And if you want to talk to me about that, I've got some great ways to talk about it, but it's not now. All right. Devastating dust. So Robert Oppenheimer, quoting the Bhagavad Gita, which is a Hindu holy book, quoted this lovely quote after seeing the first atomic, this is what he said when he first detonated the atomic bomb that he helped develop. "Now I am become death, the destroyer of worlds." And needless to say, this is the awesome power of the atomic world. What's going on there? Uranium, a specific isotope of uranium, which is a specific weight of uranium, is splitting up from a neutron bombardment and creating 3 new neutrons that can then split up those uraniums, and you keep going and you keep going, and you create the largest weapon ever created. Now, what's this to do with quantum? Well, it turns out that the way in which this nuclei splits in two is it's actually quantum mechanical tunneling. So the wave is able to get out, whereas a normal particle couldn't. So this is actually a quantum mechanical effect, and this was described using the early quantum theory. But we can also make power out of this, and that's a very, and that is actually a good output from this research, though it's hard to really compare the two in terms of pros and cons, is it? This here is a fusion reactor, and the nice thing about these fusion reactors is that they work with light isotopes like hydrogen, tritium, deuterium, and they fuse those together like the sun, and they create energy without these radioactive isotopes, these nuclear waste, which is created. And this is a picture from inside one of the tokamaks, and I had the good fortune of visiting this fusion reactor in Culham in Oxford, and the walls of this are graphite, which is carbon, my first love, after the Lord, obviously, and family. Anyway, won't get into that. Right, but also this nuclear and this radioactive stuff has been a huge benefit to our health. So quantum mechanics allows us to measure using MRI, that's the spin, didn't have time to talk about that. Also radiation therapy. And this is the nuclear reactor that we have in Australia for radioisotopes. And these radioisotopes that we produce are able to do all sorts of great things, stopping cancer. My mother actually had this iodine to kill her thyroid because she had an overactive thyroid. So without that, she would have died. So it is kind of remarkable that we have found a way to use it for good, even though you did the most destructive thing first. And one thing, I was recently visiting the UN. I saw this incredible demonstration, incredible display in the UN in Nagasaki. So it had a whole description of the 2 atomic bombs that were dropped on Hiroshima and Nagasaki during World War II. And it had a whole bunch of actual remains from the cathedral that was there. The largest group of Christians living in Asia at the time was 500 meters under the Nagasaki bomb. And so you can see here, this is actually that church that was built. And so, and this is what was left of it. And this is the melted face of one of the carvings of Mary. So, and I just loved the placing of that in the UN being like, reminding people, what are you doing? You're killing civilians, peaceful communities that you claim to represent as Christians, a lot of Christian nations as well. So that was a good reminder there, and a good reminder for non-proliferation. I've got some great books on that if you're interested. So in the last little bit here, I've been very generous with your time, thank you. We're going to talk about divine dust. And there are 10 slides left. So this is a stained glass window, and inside each of these stained glass is actually gold nanoparticles. So the red color and the yellow color you see are actually from gold and silver nanoparticles that were made and mixed in with the molten glass. And so this is actually a quantum, this quantum effect is what colors all of the stained glass windows. So obviously they didn't know what was going on with the electrons inside, but it's nice to think that there is some quantum technology there. And of course, the quote there is, "The Lord formed a man from the dust of the ground." And by man here, it actually says, we'll go into that, earth man. So we're going to get more into theology later, but let's just start with some more generic philosophy. So Einstein was quite unhappy with quantum mechanics being random, and he used quite interesting religious language here. Not because he was particularly religious himself, he kind of used it more as a way to talk about it. So quantum mechanics is very worthy of regard, but an inner voice tells me that it is not the true Jacob, the true theory. The theory yields much, but it hardly brings us close to the secrets of the old one. In any case, I am convinced that he does not play dice. You believe God who plays dice, and I am complete law and order in a world that objectively exists. So this is to do with the collapse of the wave function predominantly. He'll later go on to not like the non-locality, but anyway. And then Werner Heisenberg talked about, we can console ourselves, this is actually in a letter to Einstein, we can console ourselves that the good Lord God would know the position of the subatomic particles, thus he would let the causality principle continue to have validity. So, and actually in this case, Werner Heisenberg was religious, so he is using this in the context of his faith. And his idea here is that it may appear random to us, but that doesn't mean it's random to God. And that sort of matches with Proverbs, where it says, the lot is cast into the lap, but the decision is the Lord's alone. And I've done a talk about a year ago on randomness and purpose, and there's more details in there about that. But if you think about a lot of what we use quantum particles for is actually to create completely random things. So we actually use it for things like gambling and things where we need completely random numbers. So quantum is, in a sense, the most random thing. And, often that, we can consider that in terms of fairness as well. So this is a quote here from Matthew, "For he makes his sun rise on the evil and on the good, and sends rain on the righteous and the unrighteous." So it reveals that there is an aspect to this universe that's completely fair. When you measure it, it will always be 50-50, which is, if you've ever rolled dice incessantly to get statistics, you'll know that it takes a very long time to get things that are perfectly 50-50. And that means that there's no special treatment for Christians in the grand scheme of the created universe. And you've tried to look for, whether a Christian gets more parks than non-Christian. You will not find any evidence for that, nor will you find any evidence for anything that is statistically relevant. John Polkinghorne's written a lot more on this than I can cover. Please go there if you want to know more. He's got a nice quote here. "Quantum theory also tells us that the world is not simply objective. Somehow it's something more subtle than that. In some sense it is veiled from us, but it has a structure that we can understand." So that veiling is the fact that we don't know what the outcome of that random process will be. So that people have related that to free will and divine action. So previously, that mechanical universe of the billiard balls and everything was very deterministic. And some people have said, well, in that mechanical universe, everything is predetermined. Now, that's not quite right with chaos theory, but in quantum mechanics and chaotic systems, it reveals that we don't have a clockwork universe in the traditional sense, that there is something that, you can't predict if you open Schrodinger's cat box whether the radioactive nuclei will have killed the cat or not. You won't know that. And so some people have suggested that provides a place where there could be divine action, providence, or non-interventionism. which I am again not qualified to talk about in any detail. But it is an interesting thing to explore there. Now, and this also leaves room for things like free will and consciousness, which I won't get into as well. Again, a lot of people talk about quantum things in terms of consciousness, and I know there are some. Penrose thinks that consciousness has something to do with quantum mechanics. What we do find is that the brain is not an isolated system, and it's very hard to keep anything that is constantly being jostled in a quantum mechanical state. And so I think decoherence would make it very unlikely that brain processes would have quantum properties, though there's not a lot of evidence either way at the moment. And there's quite a lot of work done on the emergence of complexity through networking in the brain, which seems to be perhaps a better place to go forward. The other one I'll just note is that a lot of people would just like God to show themselves, and that would be great. And that would be an easy way to prove that God is there. But there is a deep way in which God is hidden in the world, and that's by design. So there's a lot of discussion of hiddenness and of this discussion of what is order and disorder. And really, I will point to things I think are beautiful and ordered, and someone else will show something opposite. So it's not very helpful. But we know that there is, in a way, this hiddenness to some of the deepest parts of our world. So quantum mechanics is inherently not something that you can, that's not deterministic. And so that non-observability is quite fascinating. And actually, John Polkinghorne will talk about that a bit when he talks about quarks, which are constructed to be unobservable as well. And, well, they might be observable, but at the moment they appear unobservable. And it's interesting to consider parts of physical theory that could be unobservable, but is still there and makes sense of our reality. And I think a lot of people have considered that the universe is also more than just matter. And so, can't get into that, but energy and matter being interchangeable in relativity is quite interesting. And also this idea that information is a key aspect of the universe that seems to be able to be uncoupled from matter in ways that would indicate that there is more going on than just materialism. And throughout history, many have thought that we are more than just the atoms we are made of. So John Polkinghorne's one example, and he talks a little bit about how, theologians have been puzzled about how things can be three in one, which is the triune God, and that has a similarity to being confused about things or the paradoxes, though I feel this argument is just talking about how things are paradoxical, so I'm not sure if there's a direct line you can draw between it, but it's a nice book to read. And Christian worldview is that God created humans from the dust, and Adam literally means earth or soil, so it's literally saying we are earth people. And it also talks about how we will return to dust, so there's this cyclic nature to it. And really, if you work through where the dust comes from, it comes from nucleosynthesis and large explosions of stars. We are created from the dust of this universe, quite literally, so that is why I called this dust of creation. Some people will argue around this many worlds interpretation, and that's often confused with the multiverse explanation for the Big Bang, or the fine-tuning of our universe. And often this argument comes around to, well, we're not very important because the universe is bigger than we thought, which I feel like isn't a very good argument because, Jennifer Wiseman puts it quite nicely here so she is the head of the Hubble Space Program and also a Christian, and she says when some people hear that the universe has been around for billions of years, they despair and feel that life must be insignificant and pointless. But our significance is not because of the tiny space and time we occupy in the universe. It is because we have a relationship with the God who is responsible for it all. I quite like. Werner Heisenberg also talks about the relationship with faith and science. In the history of science, ever since the famous trial of Galileo, it's been repeatedly been claimed that scientific truth cannot be reconciled with religious interpretation of the world. Although I am now convinced that scientific truth is unassailable in its own field, I've never found it possible to dismiss the content of religious thinking, simply part of an outmoded phase in the consciousness of mankind, a part we shall have to give up from now on. Thus, in the course of my life, I've repeatedly been compelled to ponder on the relationship of these two regions of thought, for I have never been able to doubt the reality of that to which they point. George Lemaitre was a Catholic priest, and he proposed the Big Bang Theory, but he didn't call it the Big Bang Theory. That was Fred Hoyle that was trying to mock it. He called it the primeval atom, the idea that if you wind back the clock, everything was fit inside of a single atom. This idea that the universe started from an atom, and I just love that connection. Einstein thought the universe was eternal, but George Lemaitre didn't have a problem with it having a beginning point, though he distanced himself from saying that that proves God. Bill Phillips, who I met, who won the Nobel Prize in 1997 for atom traps and Bose-Einstein condensates, is a committed Christian. I spoke to him about it, and he's from more of an evangelical tradition as well, more charismatic. So that's quite interesting as well. And he talked to me about how he loves doing Sunday school and bringing in experiments to do with the kids. Donna Strickland is another Christian who got the Nobel Prize for mode-lock lasers, which are femtosecond lasers, so 10 to the minus 15 seconds. And she talks about how in her tradition of the Uniting Churches in Canada, how she just wonders why we're inside this universe, and we keep thinking how important we are, and every so often you sit there and you think, now why are people hurtling around on this earth going around the sun, which is still just a speck in the whole blessed universe? We are so insignificant to the whole thing, and yet we keep thinking how important we all are. And so I have to think there's some reason for us specks to be on this other speck in this giant thing. I just wonder what's out there that wanted this to happen. And there's a lovely article written about how when she learnt that she was a Nobel Prize winner, she went to church the next day and she was on handing out the hymnals and also cleaning the toilets. And so she went and did that. So that's what a Christian does when they win a Nobel Prize. And she was actually still a senior lecturer at the time, and they quickly made her a professor. So that was also an interesting point there. The last one here. Often people think faith is just belief in sort of ungrounded belief, but faith is really belief in what is not seen. So this is a good quote here. Now, faith is the assurance of things hoped for, the conviction of things not seen. And so when I think of looking at the quantum realm and these things, there's things that are by definition not seen. And so in a sense, we need faith for quantum physics as well as for the metaphysical things. And scale is not important. So faith of a mustard seed, kingdom of God grows from the smallest seed. And I recommend, if anyone's not looked into the light of the world, which is Jesus, I recommend it because as remarkable as light is, he is more remarkable. And I just want to end with this prayer. Thank you for your patience with me. It's a tough topic to do the whole quantum mechanics. Let's end with this prayer so that I can remind myself of what's important. So I thank you, my Creator, that you have given me joys in your creation and ecstasy over the work of your hands. I have known the glory of your works as far as my finite spirit was able to comprehend your infinity. If I have said anything wholly unworthy of you or have aspired after my own glory, graciously forgive me. Amen. Great. That's it.